I was not yet recording, Kenya. You'll get another extra credit point. Though I'm not convinced you need it at this point. All right, we are recording. We are rocking and rolling. And so, first, let's just go over really quickly the stats from last exam. Mean was a 74%. The standard deviation, a little over 22.5%. There were 5 students who got a perfect score, so I didn't do any curving on this exam. And for those of y'all who wanted to know, there was no significant difference between the first exam and this exam, although we were kind of trending in that direction. So the t-test that I ran for it gave me a t-value of 1.41 with a p of 0.08. Had it been significant, the exam 2 performance would have been a little less than exam 1. All right, questions about the exam or anything pertaining to that?
You said that this test was going to be harder than the last test. Is this test going to be the hardest one?
This upcoming one?
Or the one we just
or...
did. Yeah, because you said this one's
no.
good. No, okay.
No.
Great.
So last year I combined what is this year's your exam 2 and exam 3 into just one exam. Last year I've split it up this year. The Anova stuff seems to really trip up people. So, I mean, the final exam is going to be a combination of everything. So I think
right.
just based off of pure numbers, it's going to be the hardest one. But I think they kind of progress in difficulty. So this next one tends to be the hardest one for most people.
Got it. Okay. Thank you.
Yes. And then you can see the actual breakout of frequencies for this exam, such that there were 20 A's on it. And then you can kind of see it drop off there. All right. This keeps giving me problems. It's going to drive me nuts. All right. We won't go over what we learned last time because last time was an exam. Here's your fun fact of the day. The technical term for fear of long words. I once had a girl in class who could actually pronounce this. Hippopotamantros.
I can pronounce it.
Oh,
I can
all
also
right.
pronounce it.
All right, give it a shot.
Quipedaleophobia.
Show off. Somebody else said
it was in an episode of Wizards of Waverly.
Yeah, that's why I can pronounce it too, because it was in Wizards of Waverly.
Wizards of Waverly Place, yeah.
Oh, okay. Is that a TV show or a movie?
TV show.
TV show.
Cool. Well, there you go. It seems kind of perverse that that would be the word for the fear of long words. All right. All right, so today we're going to be talking about Anova, the analysis of variance tests. All right, so with our t-tests, what were some of the characteristics of t-tests? Like what type of samples did we need? Or how many samples?
2.
Yeah, so we could do a 1 sample t-test, but we could also do a 2 sample t-test, but we couldn't go over 2 samples, right? So you can only compare UAH to UAB. You couldn't compare UAH to UAB to Tuscaloosa. Oh, that's good, Jay. Apparently the word for fear of palindromes is itself a palindrome. So People have humor. So yeah, we are now going to be talking about the ability to run tests. This is driving me insane. I may just go straight to the computer and lecture from behind there. But we're going to be talking about tests today to run when you have more than 2 samples, right? You can run an Anova with 2 samples, but if you wanted to be doing some sort of comparison between 3 different groups or more, you would need to run an analysis of variance. And so the goal is to determine whether the mean differences that are obtained for sample data are again going to be sufficiently large to justify a conclusion that there are mean differences between the populations from which you drew those samples, right? So this is just reiterating what we've already talked about for t-tests. But again, when we are interested in looking at differences between groups, it's not sufficient just to say, yes, there's a mean difference. We have to say, is that mean difference big enough such that we can't account for it by just by chance? All right, iPad keeps losing connection, so I'm going to transfer over just straight to the computer. But so like I said, the analysis of variance is when we're going to be using 2 or more, right? And so you can use an Anova in lieu of a t-test, and they'll give you the same result. I mean, they'll give you different numbers for the F versus T, but by and large, they will still give you the same result. All right, can you all hear me again? Perfect. All right, so we have transitioned back. We are good to go. Cool. All right, so analysis of variance is necessary to protect researchers against a type 1 error. Somebody remind me, what is a type 1 error? A false positive, exactly, yes. So a type 1 would be a false positive, a type 2 would be a false negative. And we use an analysis of variance to protect against a type 1 error because if we ran a series of what's known as pairwise comparisons, we would be essentially opening ourselves up to a type 1 error, right? If you think about the fact that a p-value of 0.05 in theory should have a 5% false positive rate, if you run 20 tests, you're going to find a false positive, right? Just by chance. And so we want to run what's known as this kind of omnibus test that we get with an Anova, such that we're running one test, which is making comparisons across all the different groups, rather than running a whole bunch of pairwise comparisons in there. So like I said, if we didn't do that, this would require a series of t-tests, right? A versus B, A versus C, A versus D, B versus C, B versus D, C versus D, rather than just having one test. And although each t-test can be done with a specific alpha level, the alpha levels accumulate over the series of tests such that we would have what's known as a final experiment-wise alpha level. And that final experiment-wise alpha level would get kind of unruly and large, right? And so this is one of the issues with what's known as data mining, right? And so there are a lot of fields that will go out and collect big samples of data and then just look for correlations in them, right? But they're increasing that experiment-wise error rate. And so a lot of medical studies will actually do this, where they'll collect a lot of longitudinal data, and then they'll just run a crap ton of correlations to see, okay, are there any correlations out there? And just by chance, you're going to find some false positives in that data, which leads you to kind of go down a rabbit hole that isn't representative of the truth. And so an Anova, or analysis of variance test, allows the researcher to evaluate all of the mean differences in a single hypothesis test using a single alpha level, thereby keeping the risk of that type 1 error rate under control, no matter how many different means we're comparing. So whether we're comparing 2 means or 100 means, that type 1 error rate remains the same. So questions about that so far, or why we even care about Anova rather than a crap ton of t-tests?
So it's basically if we have more than 2 things that we're trying to compare, and it's pretty much like a faster method to compare them all.
I didn't hear the last part. It's basically what?
Is it like just a faster method to compare sample data with like more than 2?
Well, so it's not necessarily the fact that it's faster, it's that it protects against that type 1 error rate, right? I mean, you are just running one test, but it's primarily a function of the fact that by running just one test, we're not worried about the probability increasing of getting a false one or a type 1 error or a false positive error. And so if you have 3 or more groups, it would be faster, but our primary concern is that we don't want to increase the chance that we get a false positive. Good question. All right, so again, to just symbolize what we're talking about here, an Anova is going to allow us to make a comparison between 3 different treatments, right? Or 3 different groups. So those treatments could be driving normally, driving while talking on a cell phone, and driving while texting on a cell phone. Could be UAH, UAB, and UA Tuscaloosa. But from each of these samples, we're going to have our own N, we're going to have our own mean, and we're going to have our own sum of squares. And so the test statistic for an Anova is known as an F ratio. So whereas the t-test was a T ratio, this is an F ratio. And it's a ratio of 2 sample variances. Now, for whatever reason, when the statisticians developed this Anova, they decided to reassign the name variances to mean squares. Right? So you're going to see, instead of variances, mean squares when we're using Anova, but it's conceptually the same thing. It's just variance. So don't wig yourself out. The top of the F ratio is going to be the mean squares between. And we'll go over what each of these mean in just a few minutes here. It's going to measure the size of the differences between those samples. So how much of a difference is there between the different groups? The bottom of the ratio, mean squares within, measures the magnitude of differences that we would expect if there was not any treatment effect. So how much variance is there within a group rather than just between? And students always get tripped up on which goes on top and which goes on bottom. Easiest way to remember it is B comes before W in the alphabet. So the between always goes in the numerator. The within always goes in the denominator. So again, just to represent here, the F ratio is going to be the obtained mean differences, so between the groups, over how much variability would we expect just by chance. So the variance between groups divided by the variance within groups. And this is conceptually, again, the exact same structure as for a t-test. We just have different labels, right? How much variability is there between the groups divided by how much variability would we expect just by chance? And so because we have these two different variabilities, the between treatments variance, or the mean squares between, and the within subjects variance, or the mean squares within, we can also have those variances together known as the total variability, or mean squares total. So again, this between treatments variance measures differences due to systematic treatment effects, right? So as a function of being between the groups, as well as random unsystematic factors. But the within subjects variance measures just those random unsystematic factors, right? So the bigger the treatment effect, the bigger that numerator, the bigger the F ratio, the lower that p-value. And so just as with a t-test, a large value for the F ratio is going to indicate that the obtained sample mean differences are greater than would be expected if the treatments had no effect. And again, because we've relabeled variance mean squares, it's the exact same idea, right? It's just the sum of squares of interest divided by the degrees of freedom of interest. And when I say of interest, that'll make more sense in just a few minutes. So to obtain the sum of squares and degrees of freedom values, you have to go through an analysis that separates the total variability for all of the data into two components, right? That between treatments variability and the within subjects or within treatment variability. So total, again, equals between plus within. So that between treatments variability, or mean squares between, once again, is just measuring the size of the differences between the sample means. I'm really just trying to hammer this home here. So if we have 3 treatments, each with a sample of 5 subjects, and have means of 1, 2, and 3 for each of those 3 groups, we are measuring the variability between group 1, group 2, and group 3. So by computing the variance for the 3 measures, we can measure the size of the differences. Now, although it's possible to compute a variance for the set of sample means, it's usually easier, to just use the sum t for each sample instead of the mean, and compute that variance for the set of t values. So I have mean 1, mean 2, and mean 3. I'm going to have data for each of these, whoopsies, that carried over. Ignore that line. That line doesn't exist. You have data for each of these 3 groups. And then for each of these 3 groups, you have a sum, right? That sum value is what's going to be the t. For every one of these, you're going to have a t. So you'll have t1, t2, t3, right? And that's just going to be the sum for each one of these groups. G is just going to be the grand total. So you're adding up each of those column totals. Just mathematical notation, when you see something like this, T1 plus T2 plus T3 ellipses TI, it's not talking about the wrapper. All that means is we are going to the last column, right, to the last T. So that could be 4 columns, so this would just be the 4th one, or it could be 100, and this would be the 100th, right? So for every column total, we're adding those together to get our G, our grand total. So another way, you're just adding up every X value you have, right? Every data point, add them all together. All right, questions so far? We're adding new symbology, but not new concepts, really. Did you have something in your eye, or are you confused? No, you're fine.
I had a question.
Yeah.
So when you said earlier that we were using the words mean differences and variances interchangeably?
Not mean differences, mean squares. So mean squares is what we call the variances we're going to be obtaining in the Anova.
Okay. Okay. Which is different than the mean differences.
Correct.
Got you. Cool.
I don't know what the origin of that differentiation is, but it's one we have to teach you, rather. All right. So logically, the differences or variances between the means can be caused by 2 sources, right? This is the same idea that we've been talking about up to this point. You have your treatment effects, and you have just kind of chance or sampling error. Right? There's always going to be some sampling error inherent. But the differences are also potentially partially explained by the treatment effect. Right? So are you in the driving condition, the driving while talking on the phone, or the driving while texting condition? Right? There's going to be some variability in just how people drive that by chance could explain a little bit of it. But we also have that treatment effect, which is what condition are you in, potentially explaining the overall differences. So the within treatments variability, again, that mean squares within, measures the size of differences that exist inside each of the samples, right? So if we go back to this example here, the mean squares within is just going to be looking at the variances that exist within each of these groups in there. Because each of the individuals in each one of these groups, right, all the individuals in group 1 here receive the same treatment. So differences can't be due to a treatment effect, right? It's just by chance or sampling error. Thus, those differences that we observe for that mean squares within is just due to chance or error, right? The unpredictable differences that exist between individual scores that could be a function of our methodology or just different individual differences. They're not caused by systematic factors and are simply considered to be random chance or error. All right. So again, it's the treatment effect plus the chance or error divided by that chance or error. This is just hammering home what we already talked about. When the null hypothesis is true, and there are no differences between treatments, that F ratio is balanced, right? So if there's no treatment effect, right, there's no difference between the groups, this F ratio should just be 1, right? Because you're dividing by the same thing you have on the numerator. That is when the treatment effect is 0, the top and bottom of the F ratio are measuring the same variance. And in that case, you should expect an F ratio near 1. When that sample data is near, or excuse me, when that F ratio is near 1, we're going to conclude that there's no significant treatment effect. And so again, we're going to be looking up in the table in the back of the book your F critical value. So we can't just say it's near 1, so not significant. We have to know what that exact value is, but we'll go over that in just a minute. Does that all conceptually make sense to everybody? Any questions about that?
Can you leave it on the slide for something?
Of course. All right, on the other hand, a large treatment effect is going to produce a very large value for F. Thus, when the sample data produce a large F ratio, we can reject the null and conclude that there are significant differences between treatments. This is a slide just combining everything we've already talked about. All right, so some formulas for us. So to get the total sum of squares, this should look very familiar, right? Such that the sum of squares total is equal to the sum of every x value squared minus that grand total, so G, all the x values all together, squared, divided by n, right? The number. Right? Because this is representing something slightly different, we give it a different notation, the G, but it is the same thing essentially as saying the sum of x, which you're then squaring, right? So this is pretty much the exact same thing you've already learned. The sum of squares within is the sum of the sum of squares. So if we have our three different groups, each one of those groups has its own sum of squares. This is very hard to draw on my computer keypad. But that sum of squares within is taking the sum of squares from group 1, adding it to the sum of squares of group 2, adding to that the sum of squares of group 3. Right? We're getting the sum of squares for each individual group, and then we are adding them all together. And so if you've got your sum of squares total, and you've got your sum of squares within, how do you get your sum of squares between?
Subtract the within from the total.
Yeah, exactly. So the between is just going to be the total. I'm not writing the sum of squares total, or sum of squares within, but is the total minus within, right? Because the total is just equal to between plus within. And bingo, there you go. Sum of squares between equals that sum of squares total minus that sum of squares within. However, you can also calculate it computationally, right? So computationally, and we will go over an example of this in just a minute, it's the sum of t squared divided by little n minus g squared divided by big N. So little n is the sample size for each condition. Big N is that total sample size.
Oh, what is T exactly?
Yeah, let me pull up, at least try to pull up here. the whiteboard app so we can actually go over that. 1 second here. Or not. All right, so we have our different groups, right? We have sample 1, we have sample 2, we have sample 3. All right. Within each of these samples, we have our own data all the way down here, right? This is just representing the data. And for each group, come on now. For each group, we have a total, right? And so this is the sum of everything in each of these groups, each of these conditions. Look at how straight those lines are. My goodness. All right, so you have the sum of sample 1, you have the sum of sample 2, and you have the sum of sample 3. And so when I say that the equation is the sum of t squared divided by n, that means I'm taking each of these t values, I'm squaring each of these t values, so t1 squared divided by the number of people in this group, so t1 squared divided by n1 plus t2 squared divided by the number of people in this second group plus t3 squared divided by the number of people in this group. So I'm adding all of those together. For that sum of t squared. So that sum of t squared divided by n is doing what we just did. And then we're subtracting that g, so that grand total squared divided by big N. And in this case, big N means everybody who is in our sample, right? All the individual data points. For our degrees of freedom total is just our degrees of freedom within plus our degrees of freedom between. Again, the total is always going to be within plus between. The degrees of freedom total is always going to be big N minus 1. So the total number of data points we have minus 1 and for within, you could either do it the sum of every n minus 1 Or I think the easier way to do it is just big N, so the total number of data points you have minus K. And K in this case is the number of conditions. Right? So if we have 3 conditions and 10 people in each condition, our big N would be 30, our K would be 3, and so our degrees of freedom within would be 27. Our degrees of freedom between is just that K value minus 1. So again, if we had 3 conditions, 3 minus 1 gives us 2. And a quick sanity check. So we had here, we had 30 minus 3 is 27. We had 3 minus 2, or excuse me, 3 minus 1 is 2. So 27 plus 2 is 29. And then that should add up to what we get for the total, right? And the total N, we had 30 participants because we had 10 people in each of 3 conditions. So N minus 1 would be 29, boom. We're rocking and rolling.
Excuse me, K means what again?
K means the number of conditions we have. So if it's UAH versus UAB versus UA Tuscaloosa, that would be the 3 different groups, the 3 different conditions.
Thank you.
So again, the variance, as always, is sum of squares divided by degrees of freedom for a sample. We're again just calling this the mean square, or simply MS. And so earlier when I said that the mean squares is just a function of the sum of squares of interest divided by the degrees of freedom of interest, that means to get the mean squares between, that variance between, it's just a function of the sum of squares between divided by the degrees of freedom between. To get the mean squares within, it's just a function of the sum of squares within divided by the degrees of freedom within. And then once you have those puppies, plug them in and you get your F ratio. So that mean squares between divided by that mean squares within. See, and in a way, this is actually easier than the t-test because you don't have to go and find the standard error. Right? Once you find the variances, you don't have to go find the standard deviation and then the standard error. Right? Once you got the variances, the mean squares between and the mean squares within, you're ready to rock and roll. I don't know if this is out of place. So if you look at this source table, right, and this is what you would get, or something looking like this is what you would get from SPSS when y'all do your actual labs. What you can see is how everything relates to one another, right? So the sum of squares between plus the sum of squares within equals the sum of squares total. The degrees of freedom between plus the degrees of freedom within gives you the degrees of freedom total. That mean square value is just the sum of squares divided by the degrees of freedom. So 30 divided by 2 gives you 15. 16 divided by 12 gives you 1.33. And then the F ratio is just the between mean squares divided by the within subjects mean squares. 15 divided by 1.33 gives you 11.28. And so one thing you should be prepared for on your next exam, hint, hint, is if I were to take that away and take that away and then take that away, pretend those don't exist, and said fill in the rest of this table, you should be able to do so, right? So you can't just rely moving down here because you don't know the total. And so what you do know is that 16 divided by some number gives me 1.33. I can figure out what that number is. Once I figure out what that number is, I can then add those two together to get this number. I can find that F ratio by just doing that divided by that, right? So all the information you need is here. Julie says she can't hear me. Can the rest of y'all hear me?
Yeah, I can.
Okay. Julie.
Yes.
All right. Cool. So let's work out an example. A psychologist is interested in the relationship between food color and appetite. And to explore this relationship, the researcher bakes cookies with different color icing, green, red, and blue. The researcher measures how many cookies each subject eats. The data appear on the next slide. We're going to calculate the F ratio, not ration. And we're going to use our critical cutoff for an alpha of 0.01. Excuse me. All right, so we already know that this is going to be an Anova test because we have three groups here, green, red, and blue. We're doing it at the alpha of 0.01. All right, so here's all of our data. Ignore everything below this line here for right now. Let's just look at each of these columns, right? And so, all right, so each subject is represented by a data point here. So subject 1 ate 3 green cookies. Subject 2 ate 7. 1, 0, 9. This seems very apropos. A friend of mine just baked me like 24 big cookies to help console me that my dogs aren't living with me for the next month. And I ate all of them. And so I'm very much sympathizing with this person here who ate 9 of them. All right, so you have each of these data points for each of these groups. The sum is just each of these added together for each column. So adding all of these together gives you 22, adding all of these together, 28, 17, etc. What else could we call this sum? What letter do we use?
T.
T. Exactly, yes. And then for each of these columns, we calculate our own sum of squares, all right? And so to get this sum of squares for each individual column, it's the equation we've always used, right? The sum of x squared minus the sum of x, square that, divided by n for each of these, right? Just pretend like this is, you're just doing what you've always done. So we have to get our sum of squares value for each of these columns, right? There's going to be a separate sum of squares for red, a sum of squares for blue, a sum of squares for green. And now let's get a few more data points before we move on. The sum of x squared is going to be squaring every one of these data points and then adding them all together. So 9 plus 49 plus 1 plus 0 plus 81 plus 4 plus 9 plus 16 plus 25 plus 16, or excuse me, 36, etc. Once you do all that, you should get 355. G is again going to be the sum of all of these data points, so adding up every one of these data points, or T1 plus T2 plus T3. And when you do that, you should get 67. Big N is the number of data points we have. So if you count all of these, we have 3 rows of 6 people each, gives us 18. And then little n is just the number in each column. So we have 6 in each of these columns. So little n for each one of these columns is 6. Questions about how we got anything on this table? I'm sorry. Yes. So little n is just the number in each column, right? So 1, 2, 3, 4, 5, 6, right? The big N is the total number. So we have 6 here, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Yes, yeah. There are cases in the real world where it wouldn't be equal, but I think at least, so, right, I mean, this, it doesn't have to be equal, right? In this case, they are all 6, but the only thing that would change when you're doing it is you just have to know that, you know, this could be 6, and if we're missing one here, this could be 5, and that'll just change how you get the total degrees of freedom at the end, right? And so they don't have to be equal, right? That's not going to change all that much. They have to be equal when we're doing the repeated measures in Anova that we'll do in a couple class periods. But, you know, I have it listed here as a single lowercase n, but in reality, it should be, you know, n for green equals 6, n for red equals 6, and then n for blue equals 6. Does that make sense? That's fine. Yeah, if let's say n for red, we're missing one of these and we only had 5. In that case, it would just be represented like that, and this G would now be 66 rather than 67. Nope, excuse me. Nope. The big N would be 17 rather than 18. All right. So getting ahead of myself. So our degrees of freedom total, again, is just big N minus 1. So 18 minus 1, our degrees of freedom total is 17. Our degrees of freedom within is big N minus K. So again, if we go back, we've got 3 conditions. So K equals 3 for green, red, and blue. So our big N of 18 minus 3 gives us a degrees of freedom within of 15. Our degrees of freedom between is K minus 1 for those 3 conditions, minus 1 gives us the degrees of freedom between of 2. All right, and if we add these 2 up, we get that 17, perfect. All right. This should be alternative hypothesis, not null down there. So our null hypothesis just says that all of these are equal to each other, right? That mean 1 equals mean 2 equals mean 3. Our alternative hypothesis is that they're not all equal to one another. You could have 1 higher than 2 and 3. You could have 2 higher than 3 but lower than 1, etc. We then have to find our F critical value. And so I forgot my book today, but if you go into the back of your book for the F distribution table, you'll see a column on the left and a row on top. And I don't remember which order it is. I think up top, it's the numerator degrees of freedom is what it says. On the left-hand side, it's the denominator degrees of freedom. And so in this case, for 2 between and 15 within, which would be the numerator degrees of freedom? 2, exactly, yes. So between always goes on top. 2 is always in the between is always in the numerator, within's always in the denominator. So when you do that, and you go across that top column and look for 2, you go on the left-hand side, go down, look for 15, you're going to see 2 numbers, a non-bolded one and a bolded one. The non-bolded one, as it signifies up top on that page, is for the alpha of 0.05. The bolded one will be for an alpha of 0.01. Right? That's presented on that actual page itself. You don't have to memorize that. And once we do that, for 2 degrees of freedom between and 15 degrees of freedom within, we get our F critical of 6.36. All right, so an F value above that means we reject the null. An F value below that means we retain the null. So to find our sum of squares total, we take that sum of x squared, which in this case was 355, minus that g, so again, all the values added together, squared, divided by the big N, or 18, which gives us 105.61 for our total sum of squares. Excuse me. Our sum of squares within, again, is just the sum of our sum of squares. So if we go back here, we've calculated the sum of squares for each of these individual columns, right? So for green, we do that sum of x squared minus sum of x squared divided by n, just like you've always done to get those sum of squares for each column. And that sum of squares within is just a function of the sum of squares for green plus the sum of squares for red plus the sum of squares for blue. And that gives us our sum of squares within of 95.5. All right, so we've got our sum of squares total, we've got our sum of squares within. How do we get our sum of squares between? There's an easy way and a hard way.
Subtract the total from the within.
Or subtract the within from the total. Yeah.
Yeah, that's right.
Yes. So again, remember that your sum of squares total is your sum of squares within plus your sum of squares between. If you take your sum of squares total that we already got and subtract that sum of squares within that we already got, you could get your sum of squares between. Or you could do it computationally, right? So the sum of t squared divided by n. So again, this is the green total, right? So we're taking this squared divided by the number in this group plus this squared divided by the number in this group plus this squared divided by the number in this group minus that grand total, 67 squared divided by big N. And we do that, we get 10.11. Kenya says, why is it U again? Are you talking about for these?
Yes.
Okay. Yeah, I mean, so this should just actually be mu. But I think I got lazy when I put together it before.
Thank you.
Mm-hmm. All right, so we have all of our sum of squares. We have all of our degrees of freedom. To get our F statistic, we need our mean squares. Right? And the mean squares, for whatever you're interested in, is going to be the sum of squares for that thing divided by the degrees of freedom for that thing. So if I want the mean squares between, I want the sum of squares between divided by the degrees of freedom between. So mean squares between should give me 10.11 divided by 2, or 5.06. That's my mean squares between. If I want my mean squares within, take the sum of squares within divided by the degrees of freedom within, or 95.5 divided by 5 gives me 6.37. I can put all of that in here, right? Everything we already have together. And you can see that my F ratio is 0.794. With my T critical of 6.36, do we reject the null or fail to reject the null?
Retain the null, right?
Yeah, exactly. So we retain the null or fail to reject the null hypothesis. And what this conceptually means is there is no significant difference between how many cookies people eat if they're green, red, or blue. Questions about that? Yes. So our actual F value is 0.794. Our F critical is 6.36. Because this is smaller than our F critical, we are going to retain the null hypothesis. And our null hypothesis is that there is no difference between how many cookies people eat if the cookies are green, red, or blue. Yes, exactly. Mm-hmm. Other questions? Cool. Cool. All right. So again, the null hypothesis for an Anova states that the general population, there are no mean differences among the treatments. However, the idiosyncrasy about that is if our Anova comes back such that we reject the null hypothesis, all that's saying is there is a difference, but it's not telling us where that difference is. So let's say our result had just come back significant. We reject the null hypothesis. That wouldn't tell us which cookies people ate more and which cookies people ate less. It would just say that there is a difference between those groups. And because of this, it kind of creates a problem, right? We don't want to just know that there is a difference. We want to know where that difference actually exists. So after, if we have a significant omnibus test or a significant Anova, we're going to run what's known as a post hoc test, after the fact test. Two examples would be, I never know how to pronounce this, either chef or chefies. We're going to say chef's test, and Tukey's HSD. These tests are done after the Anova, when we rejected the null, to compare the treatments 2 at a time. All right, so everything we said we didn't want to do beforehand, if we have a significant Anova, we're now going to do. Right, because this has given us, a significant Anova has given us justification to drill down into where those differences lie. That big Anova test is more robust against increasing the type 1 error rate. And as such, if it tells us, yes, there is a difference, we therefore need to look for where that difference exists. So it's the same thing. And so when we run an Anova, just like when we ran a t-test, it can tell us if there is a significant difference, but not how big that difference is, right? Not how meaningful that difference is. Therefore, we typically want to run an effect size, just as we talked about with the t-tests, right? And so t-test, we use Cohen's d or r squared. We're going to be using what's known as partial eta squared for this. The common technique for this is going to be measuring the effect size, or excuse me, it's going to be computing the percentage of variance that's accounted for by the treatment effects. All right, and so this is the partial eta squared, or the eta squared. The formula for this is the sum of squares between treatments, and now instead of the sum of squares within on the bottom, we're putting sum of squares total. All right, because we want to know what percentage of all of the variance is due to between subjects variance. So this came up a couple times on your last exam, but should you ever have an r squared or an eta squared bigger than 1?
No.
No. Why no?
Well, I don't know how to describe it. It should just be giving you a percentage. 1 would be like 100%. So you're really trying to say like how close it is to 1.
Mm-hmm.
I mean, I don't really know how to describe it, but
Yeah, no, you're exactly right. So in this case, the denominator is the sum of squares total, right? The sum of squares between is a subset of that total, but the between can never be bigger than the total. And as Caleb was saying, because we're trying to see what proportion or what percentage of the variance is explained, you can't explain more variance than there is, right? So your r squared and your eta squared should never be bigger than 1. If you ever get an eta squared or an r squared greater than 1, go back and rework your math because you done screwed up. All right, questions about what we covered today? Awesome. All right, well, if questions do come up, please let me know. I will, as with before, get a practice problem up and I will work with that soup to nuts for y'all to look over. But again, remember that what we talked about today is there's largely no difference between what we talked about today and what we've talked about in the past. It's just applying those concepts in different ways, right? And so people get a little bugged out when they see new letters incorporated into stats. But remember, what we're talking about is just kind of different applications of the same stuff we've learned. So lots and lots and lots and lots and lots and lots of practice moving forward. So if y'all do have any questions, please let me know. If you want to set up meetings, I'm more than happy to do that. Otherwise, go forth and prosper. And now you've added a whole new tool to your tool set. Jace, is that a question or are you piecing out? Oh, I think I just answered that question. He pieced out.